All right, we're back. We are Game 2005. That's Game Physics in the fall 2017 semester at George Brown. And we are Lesson 6, Part 1. We're continuing motion in 2D. And I want to kind of go through the PowerPoint, the rest of the stuff, but I want to try some stuff with you in Unity today, right? Just to talk about how it works in games. So a little bit more programming today than other days. Let's see how this works. All right, so we talked about 3 different cases. I'm just going to go back to these things right in your PowerPoint slides. We talked about the first type of case, which is this type of projectile motion, which is you either drop an object, that's one case, one part of case 1, or you throw an object, right? A kind of, kind of give an object some kind of lateral velocity. So some kind of velocity or force across the x-axis, right? So those are the 2 options. So this one will be the drop, where you're just dropping an object, right? And depending on how much velocity you give to it, like if I give initial velocity of 0, I'm just dropping it. If I push it off, or launch it off somehow straight off, then you're going to have a value here for initial velocity. Okay, that's the cases that we're talking about here.
That velocity is horizontal versus vertical?
Yeah, so you're going to have here, remember, one thing that's different about 2D motion and the rest of the stuff we're going to be talking about this semester is you're going to have components of motion, components of the physics motion that we're going to try and capture, right? So one of the components here is obviously vertical motion. That means up and down, which normally for us is acceleration due to gravity, right? So negative 9.8 meters per second squared, and that would be your A term, right? And then you're going to have some kind of velocity across the x-axis, right? Now notice it says velocity initial. It doesn't say velocity initial x, but typically velocity across the x-axis is what you're going to get, okay? In this first case, okay? So you're going to have these 2 types, and I've given you a couple of formulas. One of them is this one, if you want to find the distance. So this, the displacement, right? And this is if you want to find the height, right, then you could definitely use this one. If you want to just find the range, like the distance in R from the cliff in this particular case, then you can use this second formula. So you notice they're labeled Formula 1 and Formula 2. Let's keep going. Here's Formula 3. If you don't know, and again, if you want to use another case, right, you can also derive Formula 3 from Formula 1 and 2, where you have the final velocity. You want to find the final velocity of an object as it hits the ground, and you have the initial velocity, right? Okay, so that's the second type of formula. And we're going to sub these in during lab, okay, together. Here's another one where, as an example, we want to find the velocity, the total velocity, right, or the speed, right, where we can take the velocity in the x direction squared and the velocity of the y direction squared, take the square root of that, and of course you're going to get, like a Pythagorean distance for the value of the velocity. Okay, so more or less the magnitude of velocity across a particular vector. Okay, that's what it is. Don't worry if you don't quite understand. But here's the example I showed, right, with the first type of motion. And I'm going to just also, please be aware that you're going to also, when we go down to lab, I'm going to break it down horizontal and vertical. And in your, on your test coming up, right, the next test, we're going to do the same thing. I'll say, you know, part A and part B. And how can I do that? That means there's going to be questions that are going to have 2 parts that go together. So lots of little pools, most likely, of questions. And you're going to have to, you're going to ask, I'm going to give you a kind of one question, and the other questions are going to follow from that one. All right, that's what's going to happen, right? Or one situation and the other question. So I might ask you, what's the horizontal distance that it traveled? What's the vertical distance that it traveled? And then finally, what's the, you know, what, something else? What from horizontal and vertical, what do you know? You know, that kind of stuff. Same thing when it comes to, you know, breaking it down with different questions. Notice I'm always going to break it down between horizontal and vertical. Then we talked about the second type of motion, which is symmetrical motion, right? When you're on the ground, you're kind of on a stable surface. You're not on a cliff anymore. And you're going to launch a projectile, in this particular case, a human cannonball, But you're going to launch a projectile with some kind of angle from the ground, and it's going to hit the ground somewhere else. Okay, that's what the second type of motion is all about. And really what we're talking about is the stuff that I've talked to you about before. Equation 6 and 7 is really, everyone else okay? Okay, good. We have velocity in the x direction is v cos theta, where v is the initial velocity magnitude. So let's say, as an example, I have, this is the classic example, 100 meters per second, I'm firing a cannon. That's v, that's the 100. And then cos theta, what's the angle at 45 degrees? I fire a cannon at 45 degrees, 100 meters per second. How far does the projectile go? And if I wanted to find both of the horizontal and vertical components, then I would just take, then Vx, V on the horizontal would be V cos theta. So 100 cos 40, what's cos of 45? Anybody?
45.
Nope.
45.
Let me see.
It's 1.
Is it 1?
Thank you.
Is it 1? I didn't think it was. Let's try this out. So cos 45, thank you for that. Yeah, 0.7071, right here. 0.7, so this is 100 times, nice try. So in the x, the x component in this case would be 70 meters per second. That would be the x component, right? And the y component would be sine of 45 times the velocity, right? So 45, and we said sine, then it would be points. Did I do it wrong? No, it's the same. Yeah, because it's the same way. That's right. It's the same for both because you have a 1 root 2 triangle. That's what it really is. And where root 2 is in the on the hypotenuse, and that's the 100, right? So anyways, at the end of the day, when you look at this thing, you have symmetrical motion because you have at 45 again would be the farthest. If you want to get the farthest distance, then you want to use 45 degrees. If you want to get a higher, kind of like a higher projectile, but a shorter distance, then you could use a bigger angle, 55, 65, all the way to 90. What happens if you put it to 90 degrees? What if I shoot straight up? It's going to come down on my head, right? Whoop. That's why you don't fire. I told you don't fire your guns in a 21 gun salute above your head because you just, it's bad for you, right? Bad for your health and the health of your comrades. All right. So that's really symmetrical motion. That's the second type that we talked about, just as a review. And we have some equations. Like, for example, if I want to find the time required to travel from A to C, in this particular example, here's A, here's B, and here's C. I want to travel from here to here, and I want to find the time. And let's suppose I don't have that information, but I start off with equation number 8, which is the velocity, the final velocity, which I know what the final velocity is. You can derive equation number 9, which would be T V sine theta over gravity, right? You divide everything by G, right? And then you can take, that's just for the height, if I want to find the height, and if I want to find the total time or the time to the top, and if I want to find the time all the way to the end, then I can just double that. And that's what's happening here. So I just double the time that it takes to get to the zenith, and then I know how far it goes and how long it takes to go to the length, right? And that's equation 9 and equation 10. So 8, 9, and 10. That's why I circled these things like this for you. Okay? And if I want to find the height, just the height, and depending on what I have, I can use v squared sine theta squared over 2g. And then you can find the exact height that the particle would go if you plug all the information in there. So let's use that information I have. I have velocities 100, and I have a sine of 45, which is 0.707, right? So let's try this out. So if I go, let's say 0.707, right, times 0.707, right? You can see that I'm going to get 0.49998, right, which is 0.5 approximately, right? So I would get that for the sine theta squared, right? Here's sine theta squared, right? 0.5. And then velocity squared, 100 times 100, right? So 100 times 100, right, is 10,000, right, times 0.5, right, is 5,000 so far. That's 5,000, right? Divided by 2g, right? So divided by 19.6, right? Because 9.8 times 9.8 is 19.6 approximately. So it's 255 meters, right? That's the height of my, if I fired a cannon 100 meters per second at 45 degrees, it would go to, let's say, 255 meters and then it would fall down, right? If I did the calculations correctly. If that makes sense to you. Okay, but that's really what this is. And I might ask you a question like that. So if you see it, you just need to know how to use the right formula. So going back to our Logan's cheat sheet question earlier, I'm going to give you all the formulae, right? And then maybe what I'd probably allow you to do in the second test is put together some example questions where you can use some of this stuff, right? Because I don't want to lead you. If I put an example question, you're going to say, well, you gave us this example, we never used it, right? So that's kind of a negative too. So I might give you some stuff and then you put your own stuff together too. Almost like a half and half. All right, so that's the second type. And then we get to the third type. I'm not going to go into that one. The third type is kind of a mix of the first two, right? So we're on the cliff. We know part of it is symmetrical, this part that goes here to here, and then we have a drop. Okay, so we can almost combine both equations to do this third type of projectile motion. Okay, and this is only in 2D. So in this particular case, we're going to use the equations that we've already got and create a scenario where we can use it. Now, notice once I go to here, once I go to the quadratic formula, it's because I have no other choice. If I'm trying to find the total time it'll take for an object to hit the ground, then I need to use the quadratic formula. And of course, what we need to do is take into account all the variables we need, the height, v sine theta again times time, right? We're going to separate the time out. And then we're going to get, so if I took this equation, if I had this equation and I wanted to use this, how would I use this kind of equation in the quadratic formula? What would I do? Anyone have a clue? Well, let me zoom in here to try and get you to understand what I'm asking, right? So imagine if you've been given a formula in this thing and you have all the initial things. So for example, I know what v sine theta is. I know what my height is. I know what half my gravity is. And I want to find time, right? Well, then you can take this half gravity, right, which is negative 4.9, and sub it into what value, a, b, or c? A, right? Because it's ax squared plus bx plus c, which is the form it is, but backwards. Instead of being written ax squared plus bx plus c, it's c plus bx plus ax squared. That's what it is. That's the form that you're seeing it in reverse, right? But you can simply just reorder these things to say half gt squared plus v sine theta t plus h, which is exactly the same thing as ax squared plus bx plus c. And if you know that, then you know that this term here is a, this term here is b, and this term is c. And if you took those things, when the values that are plugged in, and put them into this formula, you could find t for time. Okay, well, let's suppose that we have the data. We know that I'm looking for 100, right? And I want to find the time it takes for the object to fall, right? As an example. Now, do I have my height? I think it was 255 meters, right? So I can plug that in. V sine theta. So with 100, right? I can take in this 255 and plug it in there into C. Here it is. And then V sine theta would be 0.707 times V, 100, so 70, right? 70t. So I'll take that 70, let's say, roughly, 70.7, but let's say 70 or 71, and plug it into B. So I would plug it in here and here, right? And minus 1/2 g, it would be negative 4.9, and I would plug it into here and here. And then I could find the total time. Okay, so that's part of what we're going to be looking at. And again, those are the three types of motion that we're going to be seeing. And I've given you a couple of additional formulas to help to find the distance from A to C and from A to B. Would be, you take the A to B plus the distance for the time from B to C, and you find the total time, right, in this particular case. Okay, I'm not going to go too much into it because that's what we really covered. And then I talked about this stuff. So how do I program that stuff? The rest, by the way, is very similar to that on the PowerPoints. If you wanted to see something, shouldn't have shown you that. But if I wanted to see something way down here, so this part, and I showed you this one as well, you can see that motion in 2 dimensions has almost this idea of, if I have 45-degree angle coming up here, that's the angle of my vector here, 45 degrees. And then when it comes down, we're going to get the reverse or the complementary angle of 45 degrees, which is just 45 degrees coming down, right? So in this particular case, sorry? They equal to 90, right? So this one here, 75, we're going to get 15 down here, right? That's the complementary angle, right? The complementary angle is the one that's coming this way, the one that's coming this way. An angle tangent to the curve, right? So that line tangent to the curve is going to produce an angle from the baseline, which is x, all the way to here. From this little angle here, it's going to be complementary of the angle of attack, if you will. If you think about this as the angle of attack or angle of incidence, if you will, at 30 degrees, then this angle here, the complement would be 60, whatever's left over, okay? Not this part under here, but the rest of it, what's left over from this one. Okay, so this part here would be the 15. That is left over from the 75. Okay. Why is that important? Because sometimes they can give us the idea how something will bounce. How will something bounce? Well, what's left over, right? And whatever's left over gives us kind of another angle, and we also will lose energy if we're going to talk about a bounce. We're not talking about energy yet. We're talking about motion. So how do I code this stuff with Unity? And let's talk about that a little bit. Remember, we talked about Unity. I'm going to bring up a Unity window. Now, you guys can't do this because you guys aren't in a classroom that has computers. But let's bring up some Unity that I want to do, right? So I'm going to bring up Unity here. We're using this as a tool only to describe motion. And one day when my Unity starts, then we'll go. Well, I'm going to use 3D. And I'm going to use 3D because it's easy, not because it's the only way I can do this. And I'm going to talk about this being game 2005. Oops. And it's the fall 2017 semester. And it's lesson, we're going to call this lesson 6. Lesson 5 and lesson 6 kind of are together, and lesson 4 too. But let's talk about this together, right? And I'm going to put this up on GitHub for those people who want to look at it later on. There will be programming questions on your next assignments. There will be something I ask you to do. Show it with code, one of those kind of things, right? Don't use Unity's built-in engine, right? If you want to, here's how you do it, kind of thing, right? So let's try this out. So I need some kind of projectile, and I want you guys to help me out here. Let's visualize. I'm not going to use any kind of built-in physics engine when we do Unity. I just want it to have some kind of motion, okay? Some kind of motion. And let's talk about this. So I'm setting up Unity in a 2/3 view right now. Always when I set up Unity, I always put it up a couple of folders. So I want to put my scripts folder in a separate spot. Here's my scripts folder. And I also want to put my scenes folder. I always kind of do this myself. And then I kind of put any kind of models that I want to have in its own folder, maybe some materials in another folder. Notice my folders are set up a little differently. Some people like the folders where they can actually see everything like this. I think that's a useless thing. So I just kind of put it like this, right? Scenes, scripts, materials, models, and then maybe I'll have other things like textures or something else. I definitely need a prefabs folder. So I'm going to kind of go in here and do a prefabs folder. Let's go prefabs. Right, so we go, there's our stuff. And I'm looking at the game screen, and I want to do my scene. And so I want to do something very simple, right, with my scene. I want to emulate 2D with 3D. And what I'm going to do is I'm going to take my camera right now, which is right now in perspective projection. Notice it says perspective. Perspective mode means exactly what you're seeing here in 3D. So I can tumble around this area and see what I want to see in 3D, but that's not really going to do me any good for what I want to do. I want to lock my camera to a 2D perspective. So I'm going to change this from perspective to orthographic, right? And when I do that, you're going to get more of a flat view, right? I'm also going to get rid of the background. I don't like, for example, that the background right now is showing me this skybox. I think skybox is useless for us. So I'm going to go to solid color, and let's just make it so we can see black in the background. That's what I'm going to do here, right? So again, if you look at the game view, it's just black now, right? And the camera is looking dead on, right? That's what it's looking at. And I want to put some shapes in here. I definitely want to put some kind of cube shape. So I'm going to kind of add that in next. So I'm going to do one of these. Again, for people who forgot how to use Unity or who don't like Unity, I apologize. But, here's my cube shape. Can I see my cube? There it is, right? And I want to use this as a platform, right? So I'm going to kind of drag it across. So I'm going to go to my, kind of my scale, and I'm going to scale this across so you can see kind of like a platform, right? There it is. And again, I'm going to go to my 2D view so you can see this in 2D, right? Kind of move this across in 2D. And in the background, you're now going to see the same kind of thing. I'm just going to zoom out here so you can see it. Here's my platform. And I'm going to move it just a little bit to the left so that way it's just kind of centered onto my screen. There we go. All right, so there it is. So now you see the platform that goes to the whole thing. So what I want to do is I want to kind of create this projectile, and I want to lock it so that it doesn't go in the Z direction at all, like it doesn't sink into the screen. It just goes in X and Y, right? Remember that when we go back to our scene view, the green arrow means on the Y-axis and the X arrow means the X-axis. We don't care about the Z-axis at all, which would be the blue arrow in normal cases. If I go back to 3D, you can see that that's the case with the blue arrow, that it goes into the screen or out of the screen. We don't really care about that, right? All we care about is this screen right now. So here we are. And all I want to do here is I want to make a projectile. So I want to start off, let's say something, and I want to move it inside this symmetrical motion. So let's try this. We're going to have a sphere that I'm going to kind of put into place here. So here's my cube. We'll just call this the platform. Right, here's my platform. Okay, and what I wanted to do is as this object moves, right, I want it to move with gravity. Now, here's the thing I'm not going to do. Although I have colliders in here on the platform and so on, I'm going to remove them. So we're not going to use, the stuff that you're going to be doing with me, I don't want you to use any kind of colliders or anything like this. We're going to remove this component. Okay, so no collider. What this does is it makes my object so you can't collide with this thing using unity physics. Okay, so you can't sit there and go, okay, I want to use unity physics to collide with this thing. We may put it back for other reasons, but not for that. Let me add another option here. Let's go in my 3D object, let's add a sphere. Right, here's a sphere. And I'm going to move this thing up so that it sits on top, or it looks to sit on top of the actual platform, right? So here's my platform. Okay? And again, this has a built-in collider that we're going to remove for that. There we go. No colliders. All right, now what I want to do is I want to move this, right, at an angle over here. I want to kind of think about this. I want to have an initial velocity, right? And we can talk about this in 2D or 3D. Now, if I play this game right now as it is, if I just press play, nothing happens, right? It just sits there. And we're going to define the motion for ourselves. Okay, that's all we're going to do, right? So help me out here. I want to make a script that I want to attach to the ball, right? So I'm going to make a new script. We're going to call this the ball controller. Balls controller, that's right. The ball controller. And we're going to attach it to the sphere. That's what it really is. It's just a ball. We'll just call it ball. So here's our sphere, ball, right? And we're going to take the ball controller and drag it across so that it's attached to our sphere. Yay. Okay. The ball controller right now, it doesn't have any kind of code. It comes with the standard Unity code, which is our start method and our update method. The update method fires every frame for people who forgot that. No, I will not update. And the start method is a thing that is being called by the constructor function, which initializes different variables. Okay, very, very simple. So what do I want to do for this ball? I want to talk about some basic things, right? In order for us to use our functions that we talked about, let's go to the first type of motion, way back over here, right? And I want to use this kind of equation. How do I take an equation and use it to move my object, right? Well, I need some kind of motion, and this is d, okay? This is the final distance, if you will, and these are vectors, right? This is a vector, initial velocity vector. So I need to break down my motion into components, right? So I need a speed across, or a velocity across the x-axis, and I need velocity across the y-axis, okay? But what if I don't have that? What if I just have a velocity, as an example, in this particular case? I don't have any x and y velocity, and I want to drop this thing as if I'm dropping it off the edge of my platform, right? So how do I, kind of simulate this type of thing? Well, first of all, we should probably change our diagram so it's not like this. And I look at this as kind of like a diagram, right? We probably want to make our ball somewhere up here sitting on some other kind of object, right? Now again, this is all motion that we're going to have based on, the object that we want, right? So let's say I'm going to put another platform in here. I'm going to put another kinds of 3D object. We'll call it a cube again. Here's my cube. And what we'll do is we'll add it so that there's a bit of a tower here. Okay. Now we have no notion of how tall this is. We have no notion of any of that stuff, right? Right now, we're going to have to figure that out when we're coding, right? Because we haven't defined anything. So here's my little tower. Let's make it a little bigger because that doesn't seem to be reflecting of how big I want to make it. Let's make it all this big, and I'll push this down a little bit, right? So let's just do this. And maybe we'll put this at the bottom just to give it some kind of the ability for us to mimic the things we need to do, right? And it's just not too much because I want to be able to see the ball. Okay, so we go. So there's the ball. Yay. And I want to put this ball on the top. Oops, undo. I want to put this ball on the top. Of course I did. Of course I did. We'll make this the tower. Thank you for that. I'm just not even looking. I mean, this is the child and this is the ball. So we're going to move it across. I thought I was selecting them together. All right, and we definitely want to see this at the very top of this thing. So we're going to simulate the first one so you can see that this is the top of the ball and we want it to fall down, right? Again, one thing we have to change is in our diagram is this next tower. We need to remove the collider. We don't have any kind of physics on this thing right now. We have a couple of options. Let's make the ground a little different. I'm going to add a material for that to make the ground look different. So I'm going to go create new material as an example. And let's just make this kind of a brownie color, something like that, a little dark brown. And I don't care about any kind of metallic looking thing. I'm going to change this from my standard shader to my specular setup, and where I'm going to reduce the specularity or the smoothness to 0, so make it very matte. Okay, that's what this does. And what I want to do now is I want to apply it to the ground, this material. So I'm just going to drag and drop it. Here we go. And so that kind of shows the difference between the ground and the tower. So I want this ball to fall. And let's go back to our code now. Let's think about what we're missing. Okay. I know this is grueling to watch, guys, but we're doing it together so I can demonstrate this for you. So I need the velocity. All right. So that's the first thing I need. But what kind of velocity I need? I have a velocity vector, right? A velocity vector. And in the first type where I'm dropping it, what's the velocity going to be? 0. My initial velocity is going to be 0. I'm just dropping the ball, right? And really, this diagram, when you think about dropping the ball, even though we're drawing it like this, isn't really like this. How should the diagram really look? It should really look, if I'm drawing the diagram, right, it should really look like this, yeah? Look like this. That's how I'm really dropping the ball, right? I'm dropping the ball. The reason why is because if you drop it here, we go into the tower. We don't want that. We just want to just drop next to the tower here, right? And probably want to give us a little bit more space. And let's just make the ball a different color too. So I'm going to add another material just to make sure that we can see the ball will be red. We'll make a red ball. Yay. A red ball. This time we'll give it a little bit of shininess because why not, right? So make it a red ball, and we'll change it again to a specular setup where we have this thing super shiny, right? And now the ball, we'll call this material, or rename this material red, and we'll name this material kind of a brown color, right? There we go. We'll take this red material, and I know this is not a Unity lesson, I'm sorry. But we'll put this over here and make it red. Yay, cool. So now when we see it, we can see that the red ball is going to fall off this white tower. Wonderful. Great setup, Tom. We're also going to save the scene. That's the first thing I like to do. I'm going to call it main. I'm going to go into my scenes view and save it. If I'm going too fast for you, by the way, and if you've never done Unity before, I apologize. But I will put this up on GitHub later on, and you will have the video to look at this. Okay, cool. So now we need to code. So I'm going to go back to scripts. Let's go to the script side. I need velocity. I need gravity, right? I need gravity. And it's going to move a certain number of pixels, right? Remember we talked about we have to frame our world a little bit, okay? And what I mean by that is there's going to be a number of pixels or meters per pixel, all right, that we have to figure out. So, or pixels per meter in this particular case. How many pixels per meter do you think we allow? And what are our Unity units? What do they mean? Well, typically they mean meters, right? Typically what they mean. So each Unity unit is usually divided into meters, all right? So we already have how fast this thing is going to fall, okay? So we can say that acceleration due to gravity, or G, right, is going to be negative 9.8, Okay, notice also, if I go back to the unity side of things, that if I was to look at the transform of this object, you can see that right now the y-axis is 5.39. And when it comes down to here, which is where I want it to stop, it's minus 2.35. So I am going in a negative direction going down for those people who forgot how unity works, right? So I want to drop this way. And so I need to define an acceleration of negative 9.8. Let's do that. And again, we're just taking it into code, just exactly what we did before. So inside we'll make a public instance variable, right? And we'll call the public instance variable acceleration, if I can spell it properly. And we're not going to spell acceleration. And we're not going to say the acceleration event, because that's not what we want. We just want acceleration. We'll make it lowercase a. Hey. Okay, so we want the acceleration by default to be a type. What type should we make this? Definitely a float, because it's going to be some kind of decimal. And it's negative 9.8. Can I assign a negative decimal number like this? Am I allowed to? Of course I am. So C sharp, right? 9.8. That's the first thing. So I got my acceleration due to gravity. Next, I need my velocity. We don't have velocity, but for now, we're going to set velocity to 0. Okay, so we're going to say public, because we're going to make other things with this. Public velocity, float, velocity, right? And we're going to make that 0.0f. Okay, we actually put 0 as well, but what the heck. And we need time, right? So time is something that we're going to track a little differently than time.delta time, which we're going to talk about, right? So we'll say public, right? And time will be in seconds, but we'll make it a float as well. So we'll say time, right? And we'll start that off at 0. Now, why is 0? Because we want to start off our time counter at 0. That's all it is. Our time is going to be a time counter. Great. We've got all of our variables here that we need, and now we need to find the destination, which is where this is going to go. Okay, but this is acceleration, this is velocity, this is time, and I need to find both my x and y components. How do I do that? Right? Because acceleration, right? Acceleration is going to be on the y-axis. It's just going to go up and down on the y-axis. So whatever I put there, it's going to accelerate down on the y-axis, okay? Just to note, just to simulate this whole thing, and if we know that our platform, in this particular case, if I look at the platform, my platform sits at approximately a y value of negative 3.48, right? And I'm going to do this again. So I'm going to go down to here, and if I frame select this one, and I want to make it as accurate as I want the lower boundaries of this thing to be this, negative 2.471. That's the value that I want the ball to stop at. Why? Because I'm simulating how it's going to hit the ground. I'm not going to use colliders here, just simulating when it stops. It's going to stop at that point, right? So that is going to be the maximum range, or the lowest part, the platform level. Yes? The limit. The ground, the limit, call it what you want. But that would be the limit, and that's where the ground position is in y. The ground y position is this, right, which is negative 2.471, right? And we'll go in there and code that. We'll hard code that one, or we can put it in as a soft code. Let's put that in there right now. All right, so let's talk about the ground position. So public, we'll say float, ground, right, is equal to a negative 2.471. We're making it public so you can change that later on, and we will. F would be nice. And that's going to set up our ground of where it is, right? So that's on the y-axis. Now, all we care about is movement in the y-axis, and I want to see a smooth change from where we are down to where the next thing is going to be. And I want to do that every update. So every update, what I want to do is, now here's the question: what's the speed of my update? How many frames per second am I firing or triggering Unity by default? Anyone know? 60, right? So 60 frames per second. That means I don't want to do 60 times. I want to skip. I want to wait, right? Now, how do I find which frame it is? I want to find the frame. I want to wait 60 ticks before I trigger off my next update. All right. How do I do that? Anyone remember how to do that? You guys taught that? How about that? All right. I could delay it. I could create a coroutine and all that kind of stuff. But I think the best thing for us to do is count our frames a little bit, okay? Just to make it easier for us to understand, right? So in our update method, and again, time.delta time, okay? And if you look what delta time is, the time in seconds it took to complete the last frame. Okay, that's what time.delta time is, time in seconds. Okay, so whatever time.delta time is, if this second, as an example, if it's whatever the time.delta time is my time in seconds, right? So if I really think about it, instead of putting an if I want to debug.log, just a second, if I want to debug.log and kind of pump out what the time.delta time is, but I do it right. And of course, debug.log doesn't work unless I convert this to a string, do it properly, right? So I just did this without any other kind of thing in here. I'm not really using this stuff yet. I want to see what this gives me. It should give me a count 1 every second if this is correct, all right? If it's not correct, it'll give me something else. Let's put this back, by the way, to the top. Okay, that's what this does. So it goes back to the starting position, which is way up here, which is where I'm going to drop the ball, right? And I haven't connected the ball, or did I connect the ball script? I did not. So the ball, here's the ball script. I'm going to drag and drop the ball script to the ball. I should see some values here. My time and my velocity, I'm not going to fill in, but you can see that some of those values I put into the default values in my code showed up here. All right, so cool. Let's see if I can count properly first. So run, and you can see that I'm not getting the values I'm looking for, right? This is the time since my last frame, the time since my last frame. That's what time.delta time is, right?
The difference between frames as opposed to fusion of time.
Right, but I don't want that. I want something else, right? So what about if I just go time.time? What's that? There's 2, right? And again, this is for you guys to know too. If I go time.time, it says the time at the beginning of this frame, read only, this is the time in seconds since the start of the game. Okay, that's good, right? The time at the beginning of the frame, right? So what I want to do is every frame, it's going to give me the next time, whatever that is. Maybe time.time is what I want, right? And again, I want to put this to toString so I can print it out because debug.log requires a string. Let's take a look at that and see if that's any better. I'm going to run this now, and let's see if I get the times ticking a little differently. So console log, and you can see that it looks like, let's clear this up again. What I'm getting is not what I'm looking for either. Does that make sense? Because if I was looking for these should be even numbers, right? These intervals that I'm getting is the time since the last frame, right? Time since the last frame, time from the beginning of the thing for each frame. I get 60 frames per second, right? So what do I got to do here? Right, time since the last frame. I'm accumulating this much time, and when I count to 60, I add one of these things, right, to the time. So this is the time between frames, right? And if I was to pause this so you can see this, right? If I go back to my console, I'm trying to figure out how to get a good timer, because if I don't have a good timer in my game, it doesn't matter, right? So notice it goes 7.39828 for those people who can't see, 7.95635. This is the time for each frame, each frame's passing, which is roughly 16 milliseconds every time, right? Well, I want to take these 60 frames and add it up to a second. That's what I want to do. So I want to take time.time, right? And I want to keep adding them until they get to 1 second. That's what I want to do. But I want to subtract the initial time, right? So time.time, the initial time since the start of the game, right? Let's try this again. Okay, so there's 0 time. Notice it says 0, 0.02. Why I say 0.02? Because again, we're roughly 16 milliseconds. 16 milliseconds every frame. That's what's happening here, right? So I'm accumulating my time until I get to 1 second, right? So when my total time is equal to 1, when this time.time is equal to 1, I want to count, right? And only then. Okay, let's try this out. So if that's true, and if I go back to my script, so the only time I want to print this out if time.time is some factor of 1, right? Like an actual 1, not point something, right? And I want to keep adding this up. I want to have almost like a variable that keeps tracking each of my total number, my total time. Call it whatever you want. Let's call it, and that's what delta time is, right? But let's just put in a total time, and we'll make it private this time because we don't have to share this one, right? So private, and we'll call it float, which is the total time, right? And we'll set it to 0 initially, 0f. And we're going to say in our update that total time, right, is plus equals to our time.time, right? The total time is equal to plus time.time. So it's going to accumulate that time. And when my total time, right, is equal to 1, right? Every time it goes to 1, as an example, then I want to reset my total time to 1. Hear me out, right? So if total time, right, is greater than or equal to 1, right, which it would be, then what I want to do is I want to tick my time factor up once. I'm going to say time is plus equals to 1. So every time my total time is greater than or equal to 1, there's many ways to do this, by the way, my time is equal to 1, right? So now I'm just ticking my clock here. So then I can actually put time in here times 2 string, if I did this correctly. Okay. Well, total time is the total accumulated time for every frame as it approaches 1, as the limit approaches 1. And notice what I said is it's greater than or equal to 1. And once it does that, time is equal to plus equals to 1. And what do we want to do with total time? Set it to 0, right? We want to set it back to 0, because otherwise what will happen is it'll keep accumulating. It'll keep accumulating forever and ever and ever. Now this may lose us some frames, just FYI, because we have some little difference between 0.02 and so on. But we're going to try and create a little timer by hand. All right, let's try this out and see if it works. If we get some whacked out value. And yeah, we're pretty good, right? But this isn't what we looked. This isn't what we're looking at. What are we seeing here? This isn't 250 seconds. What are we seeing here? So 0, 0, 0, 0, 1, 1, 1, 1. What's this? What are we getting here? Fractions of frames, right? Are we seeing this? So let me try this again. So if I go clear, and if I run it really quickly, right? You can see that there's no way that in 4 ticks, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 1, 2, 1, 2, 1, 2, 1, 2. We keep going up by approximately 1 second very, very quickly. Does anyone else have a solution to this one? We're just counting time right now, okay? Before we do anything else, because otherwise our ball is going to be totally out of whack when we make it fall, right? So time.time, again, is, like it says, the time at the beginning of the frame. This is the time in seconds since the start of the game, right? Total time in seconds, that's what it really is. So total time in seconds at the beginning of the frame. And then I'm adding them and I'm adding them. Is this really what I want? I'm adding to itself. Come on, guys. This is almost like recursively. I'm adding to the first frame the time in seconds. And the time in seconds is going to keep clicking from the time of the frame. And what's delta time? If it's time.delta time. I go time.delta time. There's 2 different things here, right? There's time.delta time. There's actually another one. And if I look at this one, it says time in seconds it took to complete the last frame. Time in seconds to complete the last frame. That's really what I want, right? Because that's what I'm looking for to do. So it takes each 0.16 seconds. Let's try this one. So let's try it again. Clear the screen, and I'll be okay. And yeah, that's better, right? So 5, 6. You can see that it's counting much slower. So, but still quite fast. Yep. Let's just use that for now, and we'll get back to it. It's just a counter, right? That's all we use. So we're going to count. It's going to be fairly fast, right? And we can see that it's counting pretty quickly. We went to 922 seconds at a very short time, which is impossible, right? And if I go back to our script for a second, let's see if that's correct. So time total time is time dot plus equals time dot delta time starting at 0. So the time between seconds will be each frame, 0.16. So when it gets to 1, we count it. Time plus equals to 1, and then total time is equal to 0. That should work. If delta time is what it's telling. Oh, I think we can use fixed delta time too. Let's try that. Fixed delta time. And there's another one. This one here, this time function, which is very important as well. It says the interval in seconds of which physics and other fixed frame rate updates, like monobehavior.fixed update, are performed. Okay? And that's one thing I could probably use. I could use fixed update instead of update. Fixed update updates everything at a fixed rate. Doesn't matter about the hardware that we're using with Unity, right? Update tries its best effort. Okay, that's what it is. But fixed update always tries to give you the same frame rate. So that might help us a little bit as well.
So you just wanted to run once every second, right?
Once every second.
Right, so couldn't you take the frame count and divide by 60?
Yes, I could, but that might not work. Well, let's try it this way first. I like your thinking. Let's try this out. So I just want to see the number that we get on the bottom here. 1, 2, here it is. No, this is working now. Look, 4, 5, 6, 7. See that number right now? That's what I want. Okay. Here it is right here. Look at the time on the bottom. You can see how it's counting properly. It's hard, but if on the bottom it's counting 16, 17, 18, 19, 20, right? Yeah, and it's also probably counting the time up here too. So 23, 24. You can see how it's counting properly. All right, so now that we have a proper counter, we can actually do the rest. We're going to take a break in a second. So now that we have this, we know that the counter is counting properly, and we're going to go per second. Now we're not changing the seconds to frames yet. We're staying back to seconds. So I want to be able to see that movement very, very slowly. 1/60th of the time we'd normally see it in the game. Okay, so you can see the motion, right? So that's our time value. Time is what we're calculating here. Now that we got our time value, we can plug in our first equation, right? Which is whatever the velocity is times time plus, and this is the velocity of movement of the actual ball, right? So we're going to say this is the y value of our ball for now, right? So how do we do this? Well, the way we can do it is we can say something like this. We can say that the transform dot position, right, is plus equals to a new vector 3 object, actually. Let's do a vector 3 object, right? And the new vector 3 object is going to be 0 on the x-axis for now. And the y is going to be our formula. This is going to be the actual distance it travels, or the new position, if you will. So we'll call this distance. We don't have that right now, but we'll put that in. Not distance 2D. It's just x the code hinting. There we go. And then we don't want it to move on the z-axis, so we'll put 0f. Okay, so 0f and 0. And we'll want our distance to be the calculation. So this is the distance that it's going to move. So we'll say distance then, right, is going to be equal to, and this is the next distance, right, is going to be equal to the current distance, or the current position in the y, right? So we're going to say the transform dot position, right, in the y-axis. This is the first part, and we're going to add, just like it says here, right, 1/2 at squared, a being acceleration and t being time, right? So we're going to say this plus, 0.5 times the acceleration, right, multiplied by the time, and then multiplied by the time again, right, because time times time. I'm not going to use any kind of other thing. Right? So times times time, that's the t squared, right? Acceleration times 1/2, right? Plus the y, plus whatever is going to be on the y. And that's going to be the total distance, right? And if I kind of look here, you can see that this is a double. And I want to, of course, cast this whole thing as a float. Otherwise, it'll give me an issue, which should ask me for one of those. There we go. That should fix it. Float. And we're going to put this in. Now, this should be very slow relative to the time. So every second it's going to tick by, it's going to move, right? And I'm moving the transformation. I'm transforming the y position, right? Now, I'm moving it plus this acceleration. The acceleration is a negative number, so it's going to move down the y-axis. That's what's going to happen here, okay? And let's see if this works, or if we have something whacked out. So we're going to go here and press plus, and it's gone, right? And it's probably moving way too fast. Let's try this again. So we're going to look at over here. We're going to motion it plus and stop it right away. Oh, okay, where is it? Oh, too late. So you can see that the y-axis is 6.51. Let's see if I can zoom into the ball for a second. So yeah, but it's way gone. And it is, the y-axis is 6.5. That's way up. We can't see it. That's why it's somewhere up here somewhere. And let's just make it so that we can see it by putting in some kind of little icon, right? So we're going to see what happened here. Let's say a purple icon or a red icon. There we go. Okay, and let's just stop this whole mess again and try it again. There's our ball, right? And we're going to click it and immediately press pause. Right, immediately, look, and it moved to 1.44. So if I double click it now, it shouldn't be that far, but oh man, it's way out of whack. It's gone. How come we can't see it? Anybody have an idea why? What was that? That's why we're very whacked, right? Z should never be moving, right? Because I didn't do anything with Z, right? And my ball, even though I told it to go, it moved on the x-axis as well. Look, on the x-axis, it's moved on a negative value, right? Well, that's because that's where it started, right? But the z-axis should definitely be 0, right? So if I go 0 on the z-axis, and if I put this, if I kind of center this, I can see my ball. There it is, right here. I can recenter it, right? There's my ball, right? But why, oh why, in my little simulation, did it go completely out of whack? I'm getting 1 counts, right? Okay, so now look, it moved 27,944 or something or another, right? Why did that happen, right? Yeah, it's going forever, right? And this is how motion would work, right? So I got to stop it. So because this is accumulating, right? Total time is completely accumulating all the time. 1, 2, 3, 4, all the way up to whatever many seconds, right? And here's my distance, right? My distance. And what I want to do before I take my distance on the y-axis and just pop it into here, I'm also adding it in here. I'm adding it onto the original position. And really what I want to do is make it equal to the original position. So that's the first change I need to make. All right. And again, for you guys to see what it is, if I want to, instead of taking my time, I know time works, and I want to know my distance. Right, here's my distance. I want to output my distance now, toString, just so I can see what my distance is, the total distance that has traveled or fallen, if you will. Right. Then I should be able to see it much slower. Yeah, now we can see it. See that? That's a little bit more reasonable. All right. It also went way out of whack over here because my x-axis right now is negative 4.89, and that's what I want to keep inside my code. Now I'm not going to normally hard code it, but we're going to put that in there. So negative 4.89. Otherwise, it'll reset to, oops. It'll reset to 0 because that's what I've asked it to do. Huh? I will set the ground. First, I want to see the motion, and it shouldn't be this fast, right? So let's see what's happening now. That's good. And that's what I want to see. I saw the motion flicker really, really fast, right? And because that's how fast this thing is falling. Because remember, I'm looking at each pixel, right, as 1 meter. Each pixel is 1 meter. And that's what our thing is right now. But if we assume that each pixel, each meter is 30 pixels, let's say for our game, which makes more sense to us, right? If each pixel is 30 meters, 30 for each one, right? Each unit is 30 units, right? Then I can sit there and I can divide by 30. So if I say take this distance, right? And this is the total distance divided by 30, right? Let's just say a number. So if I say distance divided by 30f, right? Then let's see how it goes now. So some kind of distance formula that's going to work a little slower. And you see it's going to accelerate until you can't see it anymore because it's below the screen. Let's try it again. Okay, so why did it start there immediately? I went to a y value of 0.058589, right? I started because my y value starts at 0, right? And I got to set my y value where it's supposed to be, right? So my initial position, if you will. So my y is going to be way out of whack over here. Otherwise, it's going to just start at 0, whatever it is, right? Okay, let's do that. So say my y, my initial position, we'll call it the reset position. We'll make a little function like that. So we'll say reset. And then we're done, guys, for the day. Sorry. So public or private reset function. In the private reset, we're going to say that a couple things are going to happen in our reset function. We're going to call this, right? We're going to say that our y position is going to reset to the top. Right, so whatever the y is right now, which is negative 5.39 on the positive, right? So we're going to say that transform dot position, right, just to make it easier, is equal to a new, I love when it does this to me, a new vector 3 object, and we're going to put in the x coordinate, which is this one right here, just to make sure that this handles our problem, and our y coordinate, which is 5.39, just to be accurate, 5.39f, and z coordinate at 0. So that should be our new vector starting off, our new reset position. It's going to be called on start, and then we're going to start moving from there. So that should kind of alleviate some of the problem that we're seeing. And let's see how it goes now. And again, we're starting over there. But this is good. I like the fact that it's dropping. It's just not starting where I want it to start, and I wonder why that is. So I want to put my new vector position. It must be starting the ball somewhere else. We're almost there. All I want to show you here is that the ball's motion is going to continue to accelerate as we go forward. Just to be, just to check this out, I'm going to put this ball way up here, right, for now, and then see if that makes a difference for our screen. Yeah, see, that's exactly what I was thinking is doing, right? So it doesn't really matter where I put it. But the good thing is we can pause it and put it back up where we want it to for now, and I'll figure the other part later. And if I unpause it, that was pretty whacked out. And let's try this again. Now, why is this? Why is it moving so fast from one frame to the other? We got to fix this problem, right? Because time should be a ticking. She keeps ticking, ticking as it goes. And we're starting off with a frame rate of 0, right? But you can see that our time is going to continue to accumulate time. So our time, this time.time function, is going to multiply at a crazy ass rate, right? So it doesn't matter where I start it, it just always pops down in here. And let's just make sure that, oh yeah, this is why. So in our Z axis, we'll put this over here. I don't know why that it's not doing everything the regular way. Make sure that our tower is correct. This Z axis should be 0. And let's make sure that our platform is also 0. I don't know why it went to negative, but that's fine. And scale is fine. Directional light, I don't care about that stuff. Let's try it again. Yeah, it's popping right there. So it's almost like it's resetting its position on the y-axis right in there. And it's probably because something I'm doing, I'm telling it to go there. But the, what was that? Yeah.
Your reset, you didn't actually call that at the beginning, but you're not calling it during that anything to do with your assignment.
The assigning is happening right here, right? So where I'm doing the position is the new position, the distance that I'm traveling. And the distance is going to be based on the original y position, right? So it's the original y position of the object, plus 0.5 times all this stuff, right? Now I could use order of operations to help us just to see what this is doing, because although it shouldn't matter because multiplication goes first anyway. So this is this part. So this part here is going to be added after all this, let's say, right? So I was going to put this all together for you guys. Almost done, guys. Don't worry. Bear with me. So if I just say my distance is my transform, but I'm adding something to it, see what I'm saying, James? It doesn't matter. I'm going to start off. But the problem is my transform.y starts off with whatever I've given it up here, right? Here's my transform.y, 5.39. So if I want to see my distance, my total distance string starting off, I should start off at minus 4.89. Sorry, 5.39, right? So if I was to do that, and let's just stop it on the console for a second, right? Let's see what I get. So 5.39. Then it goes to 0.17. That's in one blow, from 5.39 to 0.17. And it's probably because, I know what's happening. It's probably because my time, right, which is total time, which is my time plus equals to 1, and I'm multiplying it by time, and let's see what's happening here. Acceleration is 9.8. That's correct. 9.8 times. Let's figure this out by hand. So if I say a half of 9.8, right, which is 4.9 times 1 is negative 4.9, and that's going to be where the next position is, and that's why it's going to go. It's going to shoot right down, right? So negative 4.9. 4.9 means these are in pixels. These are in units, right? So of course it's going to move from 5 to negative 4.9, right? So if you think about it, this also has to be scaled. My 9.8 can't be, right? It's also going to be divided by 30, right? So otherwise I'm going to get too much of a big value. So let's say divided by 30F, calculate right here. Kind of ugly, but what the hell? And yes, I can put that in my start method, but I'm too lazy to do that right now. I just want to fix this. And why am I dividing by 30? I'm saying 30, it's 30 units per meter in my particular case. Okay, otherwise it's going to move 4 units every frame, which is, or every tick, which is too slow. I don't have anything else that should affect it like that. My distance is divided by 30. Yes, good. Let's try it again.
Oh, you changed it while you were running.
Yeah, that's fine. Okay, it's better. That's the kind of motion I'm looking for. As you can see, it's stepping through the next part and the next part. I'm just not seeing why it's going to, oh yeah, because of 4.1 and negative 5.3. I'm not seeing why that's doing that. I got to look at that again. Oh, my acceleration? No, my acceleration is this divided. My time is normal. My 0.5, oh, this is it. 0.5. No, 0.5 is negative 4. I can actually calculate down here. So let's just take it out. Minus 4.9. So I'm just eliminating, guys, to figure out my problem. I'm eliminating to figure out my problem. So I don't have to do this anymore. There we go. Time times time, 5.39. You guys figure it out? So, yes.
No, I just have a question.
Yeah.
Because the ball when it actually travels is, well, it's definitely decreasing on the y-axis, but it doesn't seem to be decreasing at a fixed value. Is that because it's supposed to be gaining speed as it goes down?
It's supposed to be gaining speed. It's supposed to be accelerating, right? But I just can't get it to start at, it doesn't matter where I put the ball, it starts at like in the middle of the screen. And that's something totally different than I'm used to. Because it just literally not behaving how it should. Like, I mean, even if I set this thing, let's say if I just didn't do this thing at all, right? So here, let me just show you. So if I just didn't do this thing at all, right? So no calculations on the ball, right? And I started off where I told it to do. I'm resetting it to where it is. Here's some debugging for you, right? And it should be right where I started it. Oh, where's my errors? Let's clear this bloody thing. Here it is. Okay, I'll do this one too because we don't have a distance right now. Let's try this out now. So it should stay exactly where I told it to stay. See? So that worked. But then when I activate my distance formula, this thing here, my distance, right? Where it should be next. This is the next position, the new position, if you will, right? We start off at the original position, which is starting off at, and I'm just going to put this back to where it was, which is over here, let's say. This is where it should start. So 5.34. 5.34 on the y-axis. This is the y-axis, plus the acceleration, which is negative 4.9. I chopped it down to negative 4.9 divided by 30, right? And then times time, which is time squared. Because it's always time squared. So this is what the next position is going to be in. I'm taking the current position, and I'm adding this part here, right? I'm adding to y. That's all I'm doing. I'm taking at y, and I'm adding to it, which means it's going to drop down the screen, right? Because negative, this is being a negative motion, negative 4.9 times time. Now, if I took acceleration away from this calculation, just to show you, and if I just moved it across time, so let's just take acceleration out. No acceleration. It's going to move in a very smooth arc. So it's going to be whatever y is, right? It starts off at whatever it was. Oh, wait. I just figured out what the problem is. The problem is that the new transform is going to be set to there from the very beginning because I'm using a fixed update, right? So I got to say I don't want to do it yet. It's only when time is greater than or equal to 1. That's the only time I want it to be there. So if time is greater than or equal to 1, right? So I'm not going to do the first frame for the first time. It's going to be when all this starts accelerating, right? So let's just X this in there and go to here, and that should do it. And that we should see it originally in the beginning. Let's see that. We should see a bit of a jump there. Now that's weird, right? That was kind of weird, but it worked a little better than before, right? So this first position, this transform y, so James is right. this transform y is equal to whatever the position, the original position y is, plus the acceleration for the new position, and which is what I want to do, right? But it seems that just the first jump is the thing that's causing me to have this heartache, this negative 4.9 times time, right? And then after that, it becomes smooth. So we'll figure this out. But at the end of the day, you can see that that's the original way it should work, because I'm setting the position, the new position, equal to this. Now there's other ways of doing this. I could normalize the screen so it starts off at 0, 0 at the top. Because right now what I'm doing is I'm making everything, all my transforms start in the middle of my screen. So I could change my my screen format. But the idea that I have, and if I was to change my scale of my main camera for just a second, so you can see the motion. All I want you guys to see is the motion out of all this work. But if I change my scale to 10, so let's just go to 10. And if I pull everything down to another level, so I want to pull this tower. Let's just make it so this thing here goes way down. So I'm going to move this down here. And I'm going to move this. That didn't go exactly as planned. If I move this all the way down to here like this, there's my tower. And move this way, this way a little bit more up. I'll adjust the ground number too, which is going to be now at, although I'm not really using it, at a negative 8.4. Negative 8.4 for the grounds. That's actually a better number for me to work with. And 9.8, but 8.4 is the ground level. And I want to make this fall. So let's go back. So this is my acceleration. Oh, It's not funny. And it's not actually doing this calculation here at all, because I'm setting my acceleration. It can't do this calculation on starts. I'll do that over here. In my start method, I'll say acceleration is divided equals by 30, right? F. Okay. And let's see if that works out here. I know it's kind of hard to see, but the other thing is I want to make sure that my reset position is at 10.38, just so we can see it off screen a little bit. And let's see if that works. Wow, it's really, really slow. But that's, see, this thing is how it should work. This is what I was expecting to do. It goes all the way down here at the first, right? But then the great thing is my scene will continue to accelerate every tick, right? And that's what it should do. Basically, it's counting every 30 pixels, every 30 units. So now it's working a little better. I don't know why it's jumping to that position, but I can troubleshoot that later in lab, right? But let's try that by getting rid of this. And let's try that again. That's it. That was weird. That was weird, but I don't know why it did that. That was weird. Kind of like was slow, and then it was like, whoa, which is how it should fall. So don't forget the man behind the curtain. Don't look at this distance. Look at the other parts. Like that looks like this. That part there is how it should look. So basically, it should be accelerating smoothly across, right? Unity. If I was doing this in JavaScript, yeah, right? But anyways, at the end of the day, that's the motion that we see with our time. We have to set a pixels per frame in this case, or units per frame. That's what I'm saying. So instead of moving at negative 4.8 meters, I'm saying that each meter is 30 units, right? And I could provide that. I could say like a units per meter, something like that, like a private float distance, which is like units per meter. So units per meter, right? And I could say that the units per meter is 30, right? And then I can use that as, instead of a value that I'm dividing, like over here, I could say divide this equals to units per meter, right? So that you can see that I'm just scaling it. So this is scaling the distance by, let's say units per meter. How many units per meter do I have? I have 30 units. It takes 30 of those unity units per meter, right? That's what I'm doing here. Okay, 30 unity units per meter. And then as it's falling, right, it just keeps ticking, and it's going to add the position, right, in units. This is the position in units. So whatever the position was before, I'm adding the new acceleration, which is going to be whatever it is. So negative 4.9 divided by 30, right? That's what divide equals means, guys. It's a shortcut. It's like saying acceleration is equal to acceleration divided by UPM, right? And then I'm multiplying it by time times time, right? Which is time to the power of 2, which is what I'm doing here in my equation, if you notice what's happening here. So, and the reason why this is 4.9 is because I've already incorporated the 0.5, the one half GT squared. That's what I'm doing here. I need my initial position, and then it'll fall every frame. Now, unfortunately for me, for whatever reason, it jumps from one frame to the other, which is totally unexpected. I didn't expect that. And it's probably to do something with my time function. I'm pretty sure.
Are you sure it's not when it hits 1 second that extra math starts happening?
That could be.
Right, like the first.
I like that one. That's a good one, Corey. Let's try that out. I put that in there to stop myself from having a problem. And now I'm having a problem again. All right, let's see. Let's see if you're right. Corey, you might have saved the day here. Let's see what happens, right? Time is equal to greater than 1 second. Yay. No. I like your thinking, though. That didn't make a damn difference, right? But anyways, there's something to do with that. It's something to do with my timer, I'm guaranteeing you, because that's the factor that's accelerating the object in the first place, right? Even though if I didn't put my timer in there at all, right, it would just add my acceleration as a constant value. It would just be constant motion, right? And to show you that, if I just did something like this, if I said one of these, right? And let's just put in my acceleration with this, right? You can see that now there's no acceleration. It's just negative 4.9 every frame or every second, right? If I could do that, it should just be total consistent motion the whole time, right? Let's try that again. So you can see it's my time function, because otherwise if my time function wasn't messed up, right, then it wouldn't be going like this. And we can fix my time function in a second, but all I'm looking for is a second count. That's what I want to do, like actual seconds, as opposed to timed at delta time. And then once I've done that, once I multiply it by a certain value, that's what's causing the acceleration to happen, the time function. Okay, so that should be illustrating a little bit for you. Any questions around this crazy train wreck that I've made, right? No? We're going to go over a little bit more in lab, but at the end of the day, what I want to go through it is, and I'm probably just not using the right function for Unity. There's probably a local time or some kind of regular time function that gives me just seconds. Normally, we don't count seconds in Unity, we count frames, right? And the easiest thing to do, of course, if I was to count frames, if I wanted to count frames in Unity, what I could do is I could just take the total frame count divided by 60, and that would be your seconds. But I'm using a fixed update, which usually does the trick. Well, let's see. I'll do that in lab. I don't think so. Say that again? To do what? I'll look at it for sure. That's really weird. Okay, thank you. Where is that? That's project settings. On the time. Bounce thresholds. It's not here. Thank you. But yeah, so some people are saying that it is under physics. I love learning. Time scale is 1. Fixed time step is 0.02, so I could make it 1. Okay, I'll fix that when we get to class, right? So I can change my fixed time step to 1, which would make it so that I have 1 second, which is what I wanted. Okay, that's it for me today right now. I'm going to go over this again in lab. We'll do more examples in lab, but I wanted to give you a sense of how to use Unity. It's not so hard as I made it seem. How about that? All right, thanks.
Sorry, Tom.